All right, guys, this is week 6, your science NTI lessons 7 and 8. So, before we get started, I wanted to review really quickly what you guys have learned over the last 5 weeks. So, you've been learning about waves, and you've learned now that there are two different kinds of waves, transverse and longitudinal. So let's talk about some of their similarities and then their differences. So both types of waves, transverse and longitudinal, are repeated patterns with similar properties. They both have wavelength, they both have amplitude, and they both have frequency. To measure wavelength, you measure from crest to crest or trough to trough in a transverse wave. So over here on the left. And then to measure wavelength in a longitudinal wave, you would measure from compression to compression or rarefaction to rarefaction. So wherever you see the particles close together in the model. Relationships between properties are the same. So a higher energy means a higher amplitude, and a lower energy means a lower amplitude. In this model down here on the right, I would say that this probably has a low energy. It's a low energy wave because the amplitude is low. And the reason I know the amplitude is low is because the particles where the compressions are, they're not very tight and close together. Okay. Frequency and wavelength are inversely related and vice versa. So if frequency is high, your wavelength is going to be short. But if frequency is low, then your wavelength is going to be long. Both kinds of waves transfer energy, not matter. And both occur when a disturbance is caused by a vibration. So let's talk about the differences. A transverse wave, the energy, in both waves, energy moves from one direction to the next direction, from A to B. But the matter is moved differently. So in a transverse wave, the matter is moved perpendicular to the resting position. So you can see here the particles go up, down, up, down. But in a longitudinal wave, the particles of the matter vibrate parallel. And so you can see this red dot right here. You can focus right here on this red dot. You can see that the energy is going from left to right, but the particle of matter is just kind of staying in place. Okay. So it's moving parallel instead of up and down. Transverse waves travel in the form of crests and troughs. I wish I could pause this, but you have other lessons you could go back to and review the same properties that I'm going over. The crests are the top of the transverse wave and the troughs are the bottom. And in a longitudinal wave, the wave travels in the form of compressions and rarefaction. So where the particles are tight together right here, that would be a compression. Where the particles are far apart would be rarefaction. And we learned last week that you can actually draw a longitudinal wave just like a transverse wave. So the compression is equivalent to a crest and a rarefaction is equivalent to a trough. And so I could draw this just like our transverse wave so that I could easily measure wavelength and I could easily measure the amplitude. Okay. Amplitude in a transverse wave is measured from the center line to the crest or from the center line to the trough. And then in a longitudinal wave, amplitude is measured by the degree of compression. Again, I would say that this model would be a low amplitude wave because the particles, the degree of compression, they're not very dense. If they were more dense and really thick, these compressions, if they were a little thicker, we would say that was probably a higher amplitude wave. Okay. So those are our differences between transverse and longitudinal waves. Now, this week, I want to focus on how mechanical and electromagnetic waves are alike and how they're different. So the first thing I would like us to do, we're going to read through this and you're going to record your thinking on your Google Sheet. So this video is embedded in the Google form. I would I'm going to read through this and then pause this video and go answer that question. So it says Jack and Corey went to the movies to see the newest sci-fi movie called Asteroid Battles. As they were leaving the movie, they talked about the parts they liked the most. Corey said, "I loved all the cool explosions. They were so loud and the sound made the whole theater shake. It was awesome." Jack said, "They were pretty cool, but I don't think that's very realistic. There isn't any sound in space." Well, Corey disagreed. "That's not true. If there was no sound in space, then how can the astronauts talk to the people at NASA back on Earth?" Which friend do you agree with, Jack or Corey? And explain your thinking in the Google form. So over here in your Google form, here is the prompt, and here you can type in your long answer. So if you would pause the video and go answer the question. When you're done, come back and unpause the video, and we will talk about who is correct and who is incorrect. Okay, now that you've had a chance to explain who you agree with, let's talk about who's actually right. So we're going to watch a video really quickly.
I have an issue with movies. Some of the cliches that pop up every now and then just bug me. For example, in sci-fi movies, when we are in space and something explodes, it creates a big fireball and loud, noisy explosion. It creates a blast radius that everyone can see and that we all need to get away from, even though in space sound waves don't travel and fires burn very dimly. Here's what Hollywood would have it look like. Here's what it would really look like. Now, I will admit that it looks a lot prettier with all the sound and fire, but the science nerd in me just can't let it slip by unnoticed.
So, in our scenario, who is correct, Corey or Jack? Well, according to the video, Jack would be correct because there's no sound in space. And this is because sound waves require a medium to travel through. A medium is going to be a solid, a liquid, or a gas. And sound needs that to travel from one place to another. Since there is no air in space, there's no matter, there is no medium, and the sound waves can't travel. Corey may have seen astronauts using radio waves to communicate back to Earth, but radio waves are electromagnetic waves and they do not require a medium through which to travel, which makes it possible for them to be transmitted through space. So while the movies seem really cool with those awesome sound effects and the light effects, it's not realistic because it's false science. You can't hear sound in space and light is dim. So let's talk more about the differences between mechanical and electromagnetic waves. All right, we're going to watch a bell jar experiment, and I'm going to go ahead and describe what you're about to watch. We've got two cell phones are being used in this demonstration. Phone A is kept outside of the bell, and phone B right here is inside. Phone A is going to call phone B. We can observe that phone B lights up and we can hear the ringtone. Now, back here, there's a vacuum, and it's used to remove all of the air from inside of the sealed jar. Phone A is going to call phone B. What do you think will happen when phone A calls phone B after they've taken out all the air? Let's watch and find out.
We're good. Okay, good afternoon. My name is John John Esborson. I'm here with Zach Hyde and Nate Baker at Hawkins School. It's February 24th, about 3:30 Eastern Standard Time. This setup is to illustrate the difference between a mechanical wave and an electromagnetic wave. The mechanical wave we're using is a sound wave. The electromagnetic waves we're using are both two kinds, actually visible light and the light that a cell phone uses to communicate. So what we're going to do first is I have a bell jar here which is under normal atmospheric pressure of about 100 kPa, give or take the day. And now we'll have Zach ring the phone, and hopefully we'll be able to hear the ringtone and see it light up.
So he's calling. This is phone A.
Okay. So
calling phone B, and it lit up, and we heard it.
Bell jar, but we can hear it. Now what I'm going to do is turn on this two-stage pump. It's a standard two-stage pump that you can get from any science supply company. And what it will do is reduce the pressure in this bell jar to about 3 kPa or 3% or so atmosphere, and it'll take a minute. So I'll turn on the pump.
So he's taking out the air particles.
A little pump oil never hurt anybody. Okay, so now the pump is removing much of the air molecules from the bell jar itself, and hopefully we'll be able to see the cell phone, we'll be able to communicate with the cell phone all through electromagnetic waves and visible light waves, which are a type of electromagnetic wave, but we won't be able to hear anything when the phone is activated. And we'll wait just another couple of minutes, couple of seconds actually, and hope that we've reduced the pressure far enough. I think we probably have. And okay, so go ahead and make your call. Okay. Now we see the phone in the bell jar has lit up, but we can't hear a thing.
So phone B still lit up, but no ringtone could be heard after the vacuum pump removed all of the air from inside of that bell jar. What was in the bell jar when we could hear the phone that wasn't in the jar when we could not hear the phone? If you said air particles, you're correct. What purpose do the air particles serve for a sound wave? Well, the air particles serve as a medium on which the wave travels. Sound waves travel as a longitudinal wave. Once the air was removed from the jar, what changed and what stayed the same? The light was still visible when the phone was ringing, just as it was before, but the sound was no longer able to be heard. Did anything about the phone itself change? Was the ringtone still playing even though we couldn't hear it? Of course, the phone was the same. It was still ringing. We just couldn't hear it. What did change? So what does change? The air was the medium for the sound waves, and it was removed. What does that tell us about sound waves? Sound waves need a medium. They need a solid, a liquid, or a gas to travel through. Since we could still see the light, what does that tell us about light waves? Tells us that light waves do not need a medium to travel through. Now, there are two major categories of waves: mechanical and electromagnetic. Mechanical waves always need a medium. They need matter or particles of a medium to travel. Sound waves are one type of mechanical wave. If sound energy doesn't have a medium through which to travel, then it can't move from its source to another location. That's what happened to phone B inside the bell jar once the air had been removed. Since there was no matter or medium inside the bell jar, even though the phone was ringing, there was no way for the sound energy to be transported to our ears, so we couldn't hear anything. But light waves are different. They are one type of electromagnetic wave. Although they can travel through air or other matter, they don't need a medium in order to travel. Think of space. Light from the sun is able to move through empty space to reach Earth. That is one way that scientists know that light doesn't need a medium. The same thing is true for phone B inside the bell jar with no air. Even though we couldn't hear phone B ringing, we could still see it light up. The light from phone B didn't need a medium to be transported. Mechanical waves, like sound waves, must have a medium in order to travel. But electromagnetic waves, like light, can travel whether they have a medium or not.